At the heart of the Perseus Cluster lies NGC 1275, a galaxy alive with jets of energy and mysterious cosmic storms. What makes this galaxy so extraordinary, and why does it fascinate astronomers worldwide? In this video, we'll take a closer look at its secrets. If you enjoy the journey, please like, subscribe and share, and tell us in the comments what's the most mysterious galaxy you've ever heard of. Thank you for watching. Now let's begin. The Perseus Cluster lies hundreds of millions of light-years from Earth, spread across a region of space that holds thousands of galaxies. It is one of the most massive nearby clusters, an immense concentration of matter bound together by gravity. When astronomers study the cluster, they see not only the individual galaxies that orbit within its boundaries, but also the shared envelope of gas and dark matter that unites them into a single structure. The scale of this cluster is extraordinary. Its core stretches across millions of light-years, and its total mass is measured in quadrillions of times the mass of the Sun. From the perspective of an observer, the Perseus Cluster forms a dominant presence in the sky of its region, where entire galaxies appear as if they are only small pieces of a larger design. Clusters of galaxies are the largest gravitationally bound systems in the universe. They are made not only of the galaxies themselves, but of three major components: the galaxies, the vast pools of hot plasma between them, and the invisible dark matter that outweighs the other two combined. In Perseus, all of these parts are evident. The galaxies vary in shape and brightness. Some are elliptical, others are spiral, while some show the distortions of past encounters. They move through the cluster at speeds of thousands of kilometers per second, pulled by the cluster's gravitational potential. These motions are not random, but reflect the long history of growth collisions and mergers that created the present structure. When astronomers observe Perseus in visible light, they see galaxies scattered across a wide field, some bright enough to be picked out with medium-sized telescopes. In radio and X-ray wavelengths, however, the picture is very different. There, Perseus is luminous, one of the brightest extended sources in the sky. The reason is the hot plasma that fills the cluster, heated to tens of millions of degrees Celsius. This gas emits strongly in X-rays, creating a glow that outlines the cluster as a whole. Against this background, individual galaxies are small points. Among them, one galaxy stands out not only because of its brightness, but also because of its activity. That galaxy is NGC 1275, which lies at the cluster's very centre. Before focusing on NGC 1275 itself, it is important to understand what the outer scales of Perseus represent. The cluster is a product of cosmic evolution assembled over billions of years through the merging of smaller groups of galaxies. Gravity gathered these systems, pulling them into a deeper well of potential, and the collisions of their gas heated the intracluster medium to its present high temperatures. The result is a structure that continues to grow today as new galaxies and groups fall in, along filaments of the cosmic web. This ongoing accretion makes Perseus dynamic, not static. Streams of galaxies approach from its outskirts, sometimes plunging through the center, disturbing the gas and triggering waves of energy that ripple through the medium. The Perseus Cluster is also remarkable for its central position in cosmological research. Because it is relatively close in astronomical terms, it allows detailed observations of processes that happen in more distant, fainter clusters. Telescopes such as Chandra and XMM Newton have mapped its X-ray glow in detail, while radio observatories have traced the structures inflated by jets from its active galaxies. Optical telescopes reveal the motions of its galaxies and the delicate filaments of cooler gas that stand out against the hot plasma. Together, these data create one of the clearest pictures of how clusters behave. The cluster is more than just a collection of galaxies. It is an ecosystem where energy moves from the cores of galaxies into the larger environment. Feedback from active galactic nuclei, including NGC 1275, heats the gas inflate's cavities and prevents the plasma from cooling too quickly. Without this input of energy, the hot gas would radiate away its heat and collapse, leading to a burst of star formation far beyond what is observed. Instead, the cluster balances between cooling and heating regulated by the central engines. This balance is fragile and constantly shifting, but in Perseus it has been studied in greater detail than almost anywhere else. Seen across the electromagnetic spectrum, Perseus also becomes a place of contrasts. In the optical band, galaxies glitter with starlight, some in tight groups, some stretched by interactions. In infrared, dust warms and glows, hinting at processes hidden from visible eyes. In radio, long filaments and lobes extend outward, silent evidence of forces at work. In X-ray, the hot plasma dominates, a reminder that the space between galaxies is not empty, but dense with matter heated by shocks and compression. Each window provides a new view, and together they reveal the complexity of the cluster as a whole. The gravitational mass of Perseus is immense, but only part of it can be seen directly. Most of the mass resides in dark matter, which does not emit or absorb light. Its presence is known only through its gravitational influence, which bends the paths of galaxies and holds the cluster together against the pressure of the hot gas. Without this dark matter, the cluster would not be stable. Instead, the galaxies and gas would drift apart over cosmic time. The dark matter halo of Perseus provides the deep gravitational well in which the entire system sits, anchoring both galaxies and plasma in a common structure. Studying the cluster also offers insight into the larger universe. By examining its structure, temperature, and distribution of galaxies, astronomers can test models of cosmic evolution. The patterns in Perseus echo those seen in simulations where matter flows along filaments into nodes that become clusters. It is one of many clusters in the nearby universe, but its brightness and proximity make it one of the most important laboratories for understanding how cosmic structures evolve. The Perseus cluster is not static on human timescales either. Galaxies within it continue to move, interact, and sometimes merge. Their orbits carry them through the hot plasma, stripping gas from their disks and leaving trails behind. This process, called ram pressure stripping, alters the galaxy's future evolution by removing the fuel for star formation. As galaxies fall deeper into the cluster, they are transformed, shifting from star-forming spirals to quiescent ellipticals. Thus, the cluster shapes not only the large-scale environment, but also the destinies of the galaxies within it. At the center of all this lies the brightest and most active galaxy in the cluster, NGC 1275. It dominates the core, sitting in the very heart of the X-ray emission. But before reaching that point of focus, one must first take in the scale and richness of the cluster that surrounds it. The Perseus cluster is a structure of extremes: hot and cold, bright and dark, vast and intricate. It is the framework that provides the stage upon which NGC 1275 exerts its influence, and understanding its outer extent is the first step in exploring deeper toward the active core. The space between the galaxies of the Perseus cluster is not empty, but filled with an enormous reservoir of gas. This medium is called the intracluster medium, and it is one of the defining features of all massive clusters. In Perseus, it is especially prominent. The intracluster medium consists mostly of hydrogen and helium heated to tens of millions of degrees Celsius. At such high temperatures, atoms are stripped of their electrons, leaving behind a plasma of free nuclei and electrons. This plasma does not shine in visible light, but it radiates strongly in X-rays, making the cluster one of the brightest diffuse X-ray sources in the sky. instruments like the Chandra X-ray Observatory have revealed intricate structures in this glow mapping the density, temperature, and disturbances that ripple through the plasma. The sheer amount of matter in the intracluster medium is staggering. It outweighs the mass contained in all of the galaxies of the cluster combined. This means that most of the visible or baryonic matter in the cluster is not in the form of stars but in this hot gas. It acts as a reservoir, storing material that could in principle form stars if it cooled. However, the gas does not cool easily because of the constant injection of energy from the central galaxy and its active nucleus. Instead, it remains hot and extended, shaping the entire environment of Perseus. When viewed in detail, the intracluster medium shows ripples, cavities, and shock fronts that tell a story of past events. These features are not random. They are evidence of energy injected by active galaxies, especially NGC 1275 at the core. The central black hole drives jets that inflate bubbles which rise through the plasma like buoyant balloons. As they do, they displace the hot gas, creating cavities seen clearly in X-ray maps. Around these cavities, the plasma shows edges and fronts, where the density and temperature shift. These are shock waves, the marks of violent episodes when energy was released into the medium. Over time, these disturbances distribute heat through the cluster, offsetting the natural cooling of the gas. Another property of the intracluster medium is its enrichment with heavier elements. Although hydrogen and helium dominate observations, show the presence of oxygen, silicon, iron, and other elements forged in stars. These were expelled into the cluster over billions of years by supernova explosions and galactic winds. As stars lived and died, their products mixed into the plasma, enriching it with metals that serve as traces of the history of star formation in the cluster. The pattern of abundance across the cluster reveals how galaxies have contributed material to this shared reservoir. Near the center, where galaxies are densest, the metallicity is higher, reflecting repeated enrichment. Farther out, it becomes more uniform, showing the mixing of material over time. The pressure of the intracluster medium also affects galaxies as they move through it. A galaxy traveling at thousands of kilometers per second experiences resistance from the plasma similar to the way an object moving through water feels drag. This interaction strips gas from galaxies, pulling it out into long tails. In Perseus, some galaxies show exactly this phenomenon, with streams of stripped material trailing behind them. This process removes the fuel for new stars, transforming galaxies from active star-forming systems into more quiescent ones. Thus, the intracluster medium is not passive. It is actively reshaping the galaxies that live inside it. The intracluster medium also plays a role in the transmission of sound-like waves across cosmic distances. Observations have revealed ripple-like patterns in the X-ray glow of Perseus, interpreted as pressure waves moving outward through the plasma. These waves are produced by the central galaxy's activity and spread across hundreds of thousands of light years. If one could hear them, they would correspond to a pitch far below the range of human hearing, with a period measured in tens of millions of years. Such waves show that the medium is dynamic, responding to the flow of energy from the core and redistributing it through oscillations that keep the system in balance. Because the gas is so hot, it provides a record of the energy budget of the cluster. By measuring its temperature and density, astronomers can infer the depth of the gravitational potential well that holds it in place. In Perseus, the gas reaches temperatures of tens of millions of degrees Celsius, requiring a mass of dark matter many times greater than the visible matter to contain it. Without this invisible halo, the plasma would escape into intergalactic space. Instead, it remains bound, slowly cooling at the very center while being reheated by feedback. This delicate interplay between cooling and heating is one of the central themes of galaxy cluster astrophysics. On large scales, the intracluster medium gives the cluster a smooth, rounded appearance in X-rays, but when examined more closely it is full of structure. Bright knots mark denser regions, while dark cavities mark where bubbles have displaced gas. Long, faint filaments extend outward, connected to processes occurring in and around NGC 1275. Even at distances of hundreds of thousands of light-years from the center, the plasma is influenced by what happens in the nucleus. It acts as a vast canvas upon which the galaxy at the core paints patterns of disturbance. Studying the intracluster medium also requires considering timescales far beyond human perception. The cooling time of the gas in the cluster core can be hundreds of millions of years, while the rise of bubbles inflated by jets may take tens of millions of years. Each feature seen today is part of a sequence that unfolds slowly, as events at the nucleus send waves and bubbles outward. The medium preserves this history in its texture, recording past eruptions like tree rings record seasons. By analysing the plasma, astronomers can reconstruct a timeline of activity stretching back hundreds of millions of years. The intracluster medium of Perseus is not only one of the brightest, but also one of the most carefully studied examples in the universe. It has become a benchmark for understanding how energy flows between galaxies and their surroundings. Each observation deepens the picture of how a cluster is more than the sum of its galaxies. The hot gas is the dominant visible component shaping the evolution of galaxies, storing the products of stars and acting as the medium through which energy is distributed. Without it, the Perseus cluster would not be the same system. It is the connective tissue of the cluster, a glowing sea of plasma, in which galaxies are islands and through which the processes of heating, cooling, stripping, and enrichment continue without pause. The galaxies within the Perseus cluster form a diverse population, each one a system of stars, gas, and dark matter, moving under the pull of the cluster's enormous gravity. When observed across the cluster, these galaxies appear scattered, but their distribution traces the deep gravitational potential shaped by the dark matter halo. Some lie close to the core, orbiting near the hot plasma, while others drift at the outskirts where the gravitational grip is weaker. Their variety illustrates the long evolutionary history of the cluster, where galaxies have merged, collided, and transformed over billions of years. Elliptical galaxies dominate the inner regions, large and smooth systems of old stars that long ago ceased forming new generations. Farther out, spiral galaxies can still be found, their disks showing signs of disruption as they interact with the dense environment. This mix reflects the different stages of transformation as galaxies fall into the cluster and adapt to its conditions. The orbits of galaxies in Perseus are fast-reaching thousands of kilometers per second. These high speeds arise because of the massive gravitational well in which they move. Collisions between galaxies are not always direct mergers, but even flybys at such speeds can distort shapes and strip gas. In Perseus, tidal interactions and ram pressure stripping are common. Some galaxies show faint tidal streams, remnants of past encounters, where stars were pulled into long arcs. Others show truncated disks, their gas removed by the pressure of the intracluster medium. Together, these processes alter the future of each system, gradually quenching star formation and reshaping morphologies. The central regions of the cluster are especially crowded, and here galaxies are most strongly influenced by both one another and the hot plasma. The density of galaxies means encounters are more frequent. Over cosmic time, many smaller galaxies have merged into the larger central system, building up mass and creating a layered record of past accretion events. The debris of these mergers can sometimes be traced as streams of stars or shells in the outskirts of the cluster's brightest galaxy. In Perseus, these features hint at the long sequence of interactions that have produced the structure seen today. The diversity of galaxies in the cluster is not only in their shapes, but also in their stellar populations. Elliptical galaxies are dominated by old stars, reddish in color, shining steadily, but without much ultraviolet or blue light from young stars. Spiral galaxies at the outskirts may still host star-forming regions, but as they sink deeper into the cluster, their gas is stripped and their star formation declines. Dwarf galaxies, smaller and fainter, are scattered throughout, adding to the richness of the cluster. These dwarfs are easily disrupted, and many have likely been consumed by larger systems over time. Their remnants contribute stars to the diffuse light that fills the space between galaxies in the cluster core. Perseus is also known for its seedy galaxy NGC 1275, which dominates the central region. This giant galaxy is unusual both for its activity and its complex structures, yet it is only one part of a much larger collection. Surrounding it are other bright galaxies, some large ellipticals, some with irregular appearances, and many with evidence of having interacted with the central system. These galaxies orbit within the cluster core, their trajectories shaped by the gravitational pull of the dark matter and the drag of the hot plasma. Their presence highlights the central role of NGC 1275, not as an isolated galaxy, but as the anchor in a crowded environment of smaller systems. The galaxies also provide enrichment to the intracluster medium. As stars evolve within them, they produce heavier elements which are expelled into the plasma through winds and supernovae. Over time, these contributions accumulate, giving the cluster its metallicity patterns. The rate of supernovae and the integrated history of star formation across the galaxies determine how much material has been returned to the gas. In Perseus, observations show that this enrichment is not uniform but reflects the distribution of galaxies and the mixing of the plasma. Close to the center, the metallicity is higher, matching the higher density of galaxies and their activity. Observations in different wavelengths highlight different aspects of the cluster's galaxies. Optical surveys reveal starlight tracing shapes, colors, and distributions. Infrared instruments detect the glow of dust, particularly in galaxies that still host star formation. Radio telescopes show jets and lobes from active nuclei which extend far beyond the stellar light. X-ray observations reveal the impact of galaxies on the hot medium, showing wakes and stripped tails. By combining these windows, astronomers can build a composite picture of the lives of galaxies inside Perseus. Each wavelength adds a new layer to the story, revealing the interplay between stars' gas, dust, and plasma. The gravitational environment also allows astronomers to study dark matter indirectly. By analyzing the distribution and motion of galaxies, one can infer the depth of the gravitational potential. In Perseus, the velocities of galaxies confirm the presence of a dark matter halo far more massive than all the visible matter. Gravitational lensing, where the cluster bends light from background galaxies, also provides a map of this unseen matter. These techniques reveal that the galaxies themselves are only small parts of the overall structure. They are tracers embedded in a much larger invisible framework. Some of the galaxies in Perseus are still forming stars, though at reduced rates compared to field galaxies outside clusters. Their star formation is influenced by interactions both with neighbors and with the plasma. Shocks and compressions can sometimes trigger short-lived bursts, but the general trend in the cluster is suppression. Over billions of years, the balance tips toward old red populations and the cluster becomes dominated by ellipticals. Perseus shows this pattern clearly with its bright ellipticals at the core and fewer spirals than are found in less dense regions. This transformation is one of the defining processes of cluster evolution. Beyond the visible population, faint intracluster light spreads between galaxies. This glow comes from stars that no longer belong to any one galaxy, but orbit freely in the cluster's potential. They were stripped during encounters, and mergers scattered across intergalactic space within the cluster. In Perseus, this diffuse light is difficult to detect, but it contributes significantly to the overall brightness of the core. It testifies to the long history of interactions and the continual reshaping of galaxies. Over time, more and more stars are added to this intracluster component, blurring the boundaries between individual systems. The Perseus Cluster is therefore not simply a static collection of galaxies, but a dynamic, evolving environment. Each galaxy within it is subject to the forces of gravity, gas pressure, and interaction. The variety observed today is the product of billions of years of evolution, shaped by the cluster's deep potential and hot plasma. Some galaxies are near the end of their active lives, with old stars dominating their light. Others are in transition, losing gas and fading. Together they form a record of how clusters change galaxies and how galaxies contribute to the larger structure of a cluster. In Perseus, this interplay is especially vivid, making it one of the richest laboratories for studying the evolution of galaxies in dense environments. At the very heart of the Perseus Cluster lies NGC 1275, a giant elliptical galaxy that anchors the system both gravitationally and energetically. Its central location is not accidental. Over billions of years, smaller galaxies have fallen into the cluster core and merged, building up a massive central galaxy that now dominates its surroundings. NGC 1275 is among the most luminous galaxies in the nearby universe, and it is unique for the combination of features it presents. Unlike many giant ellipticals that appear smooth and red with little structure, NGC 1275 is complex with layers of activity, filaments of gas, and evidence of ongoing interactions. Its position in the core ensures that it interacts constantly with the surrounding intracluster medium, and its active nucleus influences the gas on scales of hundreds of thousands of light years. The galaxy does not exist in isolation, but rather as the central hub of a dense environment. Surrounding it are many smaller galaxies orbiting in the cluster core. Some of these have been or are being consumed, contributing stars' gas and dark matter to the growing central system. Observations reveal tidal features, streams of stars and disrupted companions, all signatures of ongoing accretion. In this way, NGC 1275 continues to evolve, growing larger as it cannibalizes neighbors. This process is common in massive clusters, where the central dominant galaxy grows at the expense of smaller systems, but in Perseus it is particularly visible due to the detail available to modern instruments. NGC 1275 is also unusual in that it contains not only an old population of stars, but also evidence of younger stellar groups. While most giant ellipticals have long ceased forming stars, the central activity in NGC 1275, coupled with the inflow of gas from the intracluster medium and captured galaxies, provides fuel for new star formation. Observations in ultraviolet and infrared light show regions of younger stars embedded in filaments of gas. This indicates that even in such a dense and hostile environment, star formation can proceed under the right conditions. These young stars add to the complexity of the galaxy's stellar population, making it a rare example of a massive elliptical with ongoing activity. The location of NGC 1275 in the cluster core also subjects it to strong interactions with the hot plasma that fills the region. Gas cools from the intracluster medium and flows inward, condensing into filaments and clouds. Some of this gas is consumed in star formation, while some is directed toward the central black hole feeding its activity. In return, the black hole injects energy back into the medium through jets and bubbles. This cycle of inflow and feedback ties NGC 1275 directly to the state of the surrounding cluster gas, linking the fate of the galaxy to that of the cluster environment. In Perseus, this feedback loop has been studied in exceptional detail, making NGC 1275 a key system for understanding how galaxies and clusters co-evolve. From a structural point of view, the galaxy has an extended halo of stars that blends gradually into the diffuse light of the cluster core. This halo contains debris from past mergers, with shells and faint arcs visible in deep imaging. Such structures are the remnants of galaxies torn apart and absorbed their stars dispersed into the outer halo. Over time, these features will fade as the stars mix into a smooth distribution, but for now they provide a record of the galaxy's assembly history. The central regions of NGC 1275 are denser, with a bright stellar bulge surrounding the active nucleus. Between these extremes, lanes of dust cut across the galaxy's light, giving it an irregular appearance in optical images. These dust features are rare in ellipticals, suggesting that the material was acquired through mergers or accretion. Their presence complicates the appearance of the galaxy and points to a history of capturing gas-rich companions. Another defining aspect of NGC 1275 is its role as a powerful radio source. In radio wavelengths, it is one of the brightest objects in the sky, known historically as Perseus A. This emission arises from jets powered by the central black hole, which inflate lobes of relativistic plasma extending tens of thousands of light-years into the cluster medium. These lobes carve out cavities in the hot gas clearly visible in X-ray images as dark regions where the plasma has been displaced. The alignment of the radio lobes with these cavities demonstrates the impact of the galaxy's nucleus on the intracluster medium. Few systems illustrate this connection as clearly as NGC 1275, making it a cornerstone in the study of feedback. In addition to its energetic output, NGC 1275 shows evidence of ongoing accretion of smaller galaxies. One striking example is a high-velocity system seen projected against its core. This system is moving at thousands of kilometers per second relative to the main galaxy, likely passing through the cluster core along a plunging orbit. Although not physically merging at the moment, its presence demonstrates the complex dynamics of the cluster center, where galaxies cross paths and interact frequently. Such encounters can deposit additional gas and stars into NGC 1275, further enriching its structure. The galaxy also lies at the peak of the cluster's X-ray emission, directly at the bottom of the gravitational potential well. This makes it a natural site for the accumulation of cooling gas from the intracluster medium. Observations show filaments of cooler gas extending from the galaxy into the surrounding plasma, suggesting a direct connection between the two. These filaments are stabilized against collapse by magnetic fields and turbulence, allowing them to persist over long timescales. They serve as conduits channeling material toward the central regions where it can fuel star formation and black hole accretion. In turn, the black hole's feedback regulates the amount of cooling, preventing a runaway flow. This balance between cooling and heating is one of the defining characteristics of NGC 1275's central role in the cluster. The luminosity of the galaxy extends across the spectrum from radio to X-ray. In optical light, the starlight dominates, but embedded within it are dust, lanes, filaments, and young stellar clusters. In infrared, warm dust and star-forming regions are visible. In radio, the jets and lobes stand out, tracing the impact of the active nucleus. In X-rays, the surrounding plasma glows with cavities carved by outbursts. Together, these observations provide a multi-wavelength picture of a galaxy that is both extraordinary and central to its environment. Unlike most ellipticals, which appear quiescent, NGC 1275 is alive with activity, each wavelength revealing a different aspect of its complex life. Placed in the broader context of galaxy evolution, NGC 1275 exemplifies how central galaxies and clusters grow and maintain activity over long timescales. It is both the product of past mergers and a driver of ongoing change in the cluster. Its gravitational influence shapes the orbits of nearby galaxies. Its feedback regulates the temperature of the intracluster medium. Its filaments and dust reveal the cycling of material between galaxy and cluster. Observed in detail, it provides one of the clearest cases of how a single galaxy can anchor and influence a structure as vast as the Perseus Cluster. Surrounding NGC 1275 is an immense halo of stars and diffuse light that extends far beyond the visible boundaries of the main stellar bulge. This halo is the accumulated product of countless mergers and tidal interactions over billions of years. As smaller galaxies have been drawn into the gravitational well of the central system, their stars have been stripped and dispersed, forming a smooth, faint envelope that stretches across hundreds of thousands of light years. The halo blends into the intracluster light, a diffuse glow created by stars that no longer belong to any one galaxy, but orbit freely in the cluster's gravitational potential. In the case of Perseus, this extended halo is particularly prominent, demonstrating the long history of growth that has built up NGC 1275 into the dominant galaxy at the cluster's core. When studied in optical light, the halo appears faint, requiring long exposures and sensitive instruments to detect its outermost reaches. The stars in this halo are predominantly old, low-mass stars that emit a steady but subdued glow. Their presence adds little to the overall luminosity compared with the bright central bulge, but collectively they represent a significant fraction of the galaxy's mass. Embedded within this halo are streams and shells, the fossil traces of past mergers. These structures are the result of smaller galaxies being torn apart by tidal forces and their stars being spread across the outer regions. Over time, these features will smooth out, leaving an even distribution, but while they persist, they provide clues about the sequence of events that have shaped the central galaxy. The halo is not uniform in its structure. In some directions it shows faint extensions, while in others it appears more concentrated. This asymmetry reflects the complex history of accretion. Galaxies that fell in along different orbits contributed stars at different velocities and angles, leading to a patchwork of overlapping distributions. Astronomers can trace these differences through careful mapping, using deep imaging surveys that capture the faintest features. Such studies reveal that NGC 1275's halo is still being built, with fresh infall of material continuing to contribute. This ongoing assembly is consistent with the role of central galaxies and clusters, which grow gradually over cosmic time by cannibalizing their companions. Within the halo, globular clusters are scattered in large numbers. These compact spherical collections of stars are among the oldest components of a galaxy, and in NGC 1275 they are especially numerous. Some are remnants of the galaxy's earliest epochs, while others may have been captured from merging companions. Their distribution extends far into the halo, tracing its reach, and adding to the evidence of an active accretion history. By studying these globular clusters, astronomers can estimate the timescales of past interactions and the amount of mass contributed by smaller galaxies. The globular cluster system of NGC 1275 is unusually rich, reinforcing its status as a central dominant galaxy in a massive cluster. In addition to stars, the halo contains gas that has been accreted from the intracluster medium or stripped from galaxies. Much of this gas is too diffuse to form stars and remains in a hot or warm state, blending with the plasma that fills the cluster. However, in certain regions, denser clouds can cool and condense, forming filaments that extend toward the central galaxy. These structures are stabilized by magnetic fields and turbulence, preventing them from collapsing immediately. Instead, they hang suspended in the halo, sometimes forming sites for new star formation. Their presence is another indicator that the halo is not static, but an active participant in the cycling of matter between galaxy and cluster. The dynamics of the halo also influence the orbits of nearby galaxies. As they pass close to NGC 1275, their stars and gas feel the pull of the extended mass distribution. This can alter their trajectories, leading to further interactions and eventual mergers. The halo therefore acts not only as a record of past accretion, but also as a driver of future growth. Its gravitational influence extends far, shaping the cluster core in ways that go beyond the visible galaxy itself. Over time, more galaxies will be drawn in their material, adding to the halo and further enhancing its size and mass. Observations in different wavelengths reveal complementary aspects of the halo. In visible light, stars dominate with faint streams and shells visible against the background. In infrared, cooler stars and dust can be detected, showing the remnants of more recent accretion events. In X-rays, the hot gas component becomes visible, mingling with the intracluster plasma. In radio, the impact of the central jets can be traced as they inflate cavities and push against the halo gas. Each wavelength provides a layer of information that, when combined, paints a picture of a structure that is both ancient and still evolving. The halo also plays a role in shielding and channeling material toward the central regions. As gas flows inward from the cluster medium, it must pass through the halo. Here, magnetic fields and turbulence can influence its path, shaping filaments and guiding them toward the nucleus. In this way, the halo acts as an intermediary, linking the large-scale environment of the cluster with the central activity of the galaxy. Without this connection, the feedback loop between black hole and cluster medium would be less direct. Instead, the halo provides the structures through which matter and energy flow. In cosmological terms, halos like that of NGC 1275 are expected to grow continuously as clusters accrete new material. Simulations show that central galaxies in massive clusters will continue to increase in mass for as long as the universe allows infall from surrounding filaments. Perseus, being one of the largest nearby clusters, offers a clear example of this process in action. The halo of NGC 1275 is already vast, but it is not finished. New mergers will add to it, and its faint glow will continue to expand, recording each event in subtle layers of starlight. The outer halo is therefore not just a backdrop, but a dynamic component of the galaxy. It records the history of growth, influences current interactions, and sets the stage for future evolution. Its stars shine faintly, but together they carry the story of billions of years of assembly. Around NGC 1275, this halo extends like a diffuse memory of all the galaxies that came before, blending into the light of the cluster core, and reminding observers that the central galaxy is both a product and a driver of the environment in which it resides. Cutting across the bright starlight of NGC 1275 are dark irregular streaks that mark the presence of dust lanes. These features are striking because they are unusual in giant elliptical galaxies, which are typically smooth, uniform, and free of large amounts of dust. In NGC 1275, however, the dust is evident, winding across the galaxy in tangled threads, and absorbing the background light to create patterns of contrast. The dust itself is made of tiny solid particles, primarily silicates and carbon compounds that condensed in the outflows of dying stars or were carried in by smaller galaxies. Their presence indicates that NGC 1275 has captured or merged with gas-rich companions, bringing fresh material into its system. These lanes are irregular, fragmented, and in some places surprisingly dense, blocking significant amounts of starlight and giving the galaxy its mottled appearance in optical images. The arrangement of the dust lanes suggests a complex history. They do not form a simple disk as is sometimes seen in other galaxies that have acquired gas. Instead, they twist and branch with filaments extending at different angles. This irregularity points to recent accretion events where the incoming material has not yet settled into equilibrium. The orbits of the dust clouds are misaligned with the main stellar body, further evidence of their external origin. As time passes, gravitational forces and collisions between clouds may cause the dust to sink toward the center and redistribute, but for now it remains in disrupted patterns. The contrast between the smooth halo of old stars and the sharp edges of the dust lanes underscores the difference between ancient stable components and recently added material. Dust plays an important role in shaping the galaxy's internal processes. It can shield gas from the intense radiation of nearby stars and the cluster environment, allowing cooler pockets to persist. Within these regions, molecular clouds can form, providing sites for new star formation. Observations show that some of the dust lanes are indeed associated with regions of cooler gas, traced by emissions from molecules such as carbon monoxide. These regions mark potential nurseries where stars may still be forming even in the heart of a galaxy, usually considered quiescent. Thus, the dust lanes not only alter the galaxy's appearance, but also sustain the processes of starbirth. The origin of the dust in NGC 1275 is tied to its interactions with other galaxies and with the intracluster medium. Some of it likely comes from smaller galaxies that have been disrupted and absorbed. Their interstellar material, once organized in disks or clouds, is stripped and stretched into filaments as it merges with the larger system. Other dust may come from gas cooling out of the hot plasma that surrounds the galaxy. As gas cools, heavier elements can condense into solid grains, contributing fresh dust to the system. Supernovae within the galaxy itself also inject dust into the environment, although this is a smaller contribution compared with what can be delivered through accretion. The dust lanes are most apparent in visible light where they block the glow of stars behind them. In infrared wavelengths, however, the dust itself emits glowing faintly as it is warmed by starlight and other sources. Observations in infrared reveal the distribution of the dust more completely, showing that it is widespread and not limited to the most obvious dark lanes. This combination of absorption in visible light and emission in infrared makes dust a powerful tracer of processes occurring within the galaxy. By studying it across different wavelengths, astronomers can map the flow of material and understand the interplay between stars' gas and the cluster environment. Embedded within some of the dust-rich regions are young star clusters, bright and compact groups of blue stars. Their presence confirms that star formation is active in places where dust and gas coexist. These clusters are relatively small compared with a vast scale of NGC 1275, but they stand out because they are unusual for such an old galaxy. They suggest that the dust lanes are not static but are actively feeding processes of stellar birth. The young clusters provide light that illuminates the dust from behind, highlighting its irregular edges and wispy structures. Together, dust and stars create a layered appearance with old starlight as a background, dark lanes as veils, and young clusters as sparks of new activity. The dust lanes also influence the galaxy's central activity. As gas and dust flow inward, some of it can reach the vicinity of the central black hole. This provides fuel for accretion, which in turn powers the jets and feedback that affect the surrounding cluster. In this way, the dust lanes form part of the larger cycle of material in NGC 1275, linking outer accretion events with the processes at the core. They are not just superficial features, but part of the pathway through which matter moves across scales of tens of thousands of light years. The shapes of the dust lanes also reveal the influence of the galaxy's gravitational potential. Some lanes appear to curve and spiral, shaped by the pull of the central mass. Others are stretched in straight lines, likely the result of tidal forces acting on infalling material. These patterns reflect the interplay between orbital motion turbulence and gravitational settling. They hint at the dynamic state of the galaxy where equilibrium has not yet been reached. The irregularity of the lanes suggests that the processes feeding dust and gas into the galaxy are ongoing, with new material still arriving and being mixed. Deep imaging has revealed that some of the dust features extend beyond the central bulge, reaching into the halo where they blend with filamentary gas structures. This suggests a connection between the dust lanes inside the galaxy and the larger-scale filaments stretching into the intracluster medium. Material may be funneled inward along these filaments, carrying dust with it. In this way, the dust lanes represent the inner continuation of processes that begin far outside the galaxy, linking cluster-scale flows to the heart of NGC 1275. The persistence of dust in such a hostile environment is itself remarkable. The hot plasma of the intracluster medium can erode dust grains through collisions with energetic particles, a process called sputtering. Despite this, significant amounts of dust are present in NGC 1275, suggesting that it is being replenished faster than it is destroyed. This replenishment likely comes from the continuous inflow of material from smaller galaxies and from the cooling of cluster gas. The balance between destruction and creation ensures that dust lanes remain visible, even though individual grains may survive only for limited timescales. In summary, the dust lanes of NGC 1275 are a window into the complex processes of accretion, star formation, and feedback that shape the central galaxy of the Perseus Cluster. They are not typical for giant ellipticals, but in this case they reveal an active history and ongoing transformation. Through their irregular patterns, they tell of mergers and inflows. Through their shielding and cooling, they enable new stars to form. Through their inward motion, they feed the nucleus. They are both scars of the past and pathways to the future, integral to the story of how NGC 1275 continues to evolve at the heart of its cluster. Stretching outward from the core of NGC 1275 are some of the most visually striking features of the galaxy, the star-forming filaments. These delicate thread-like structures extend for tens of thousands of light years, suspended against the glow of the hot intracluster medium. They are narrow, elongated streams of cooler gas threaded with magnetic fields and dotted with young star clusters. Their presence is unusual, for in most central cluster galaxies, the hot plasma prevents such fragile structures from surviving. In Perseus, however, these filaments persist, providing a rare opportunity to observe the processes of cooling and star formation directly in the hostile environment of a cluster core. The filaments appear as long, reddish streams in deep optical images, often branching or curving in arcs. They are made primarily of hydrogen gas at temperatures far cooler than the surrounding plasma. Spectroscopic studies reveal that they emit light characteristic of ionized hydrogen, as well as molecular signatures that indicate the presence of dense cold clouds within them. These cold regions are where new stars can form, and indeed, observations confirm that compact blue clusters of young stars are often located along the filaments. The contrast is striking. Tiny pockets of stellar birth embedded within structures extending across tens of thousands of light years, all surrounded by an environment heated to tens of millions of degrees Celsius. The survival of these filaments is one of the puzzles of NGC 1275. In principle, The hot intracluster medium should evaporate or destroy them on timescales far shorter than their observed lifetimes. The fact that they remain intact suggests that stabilizing mechanisms are at work. Magnetic fields are thought to thread the filaments confining the gas and preventing it from dispersing. Turbulence within the surrounding plasma may also help insulate them. Whatever the exact balance of forces, the result is that these filaments endure long enough to form stars, adding new stellar populations to the central galaxy. The distribution of the filaments is not random. Many of them extend radially outward from the galaxy's core, following paths that suggest a connection to the rising radio bubbles inflated by jets from the central black hole. As these bubbles rise through the intracluster medium, they lift cooler gas from the galaxy's center, stretching it into long threads. In this way, the activity of the nucleus helps to create the very structures that later fuel star formation. The filaments therefore illustrate the complex feedback loop in NGC 1275, where energy injected into the cluster gas paradoxically helps seed conditions for new stars. Closer examination of the filaments reveals clumps and knot sites where the gas has cooled and condensed to higher densities. Some of these knots are associated with star formation visible as compact clusters of hot young stars. Others may be precursors where molecular clouds are forming, but stars have not yet ignited. These star clusters that form within the filaments are small compared with the mass of the galaxy, but they are important for understanding how gas cycles between different phases. Their light also provides a way to trace the history of the filaments, as the ages of the stars reveal when the gas cooled and collapsed. The lengths of the filaments are extraordinary. Some stretch for more than 50,000 light-years, nearly comparable to the diameter of the Milky Way. Despite their fragility, they remain coherent over these distances, testifying to the strength of the forces that hold them together. Their narrow widths, often only a few hundred light-years across, make them appear like threads drawn taut across the surrounding glow. This geometry emphasizes their contrast with the diffuse intracluster medium, highlighting the sharp divide between cool and hot phases of gas in the cluster core. Observations across multiple wavelengths deepen the picture of the filaments. In optical light, their hydrogen emission lines are bright, tracing the ionized gas. In infrared, molecules such as carbon monoxide are detected, confirming that cold, dense regions are present. In X-rays, faint emission reveals interactions between the filaments and the surrounding plasma, as well as evidence that they are embedded in hotter envelopes. In radio wavelengths, weak continuum emission suggests that magnetic fields play a role in their stability. The combined datasets show that the filaments are multi-phase structures with cold molecular cores, warm ionized envelopes, and magnetic scaffolding, all contributing to their persistence. The star formation within the filaments is not uniform. Some regions show clusters of young stars, while others remain devoid of obvious stellar activity. This variation likely reflects differences in density cooling rate and shielding from the intracluster environment. It may also indicate that the filaments are at different stages of evolution, with some just beginning to condense, while others have already produced stars. The result is a patchwork of activity with stellar birth, occurring in localized bursts across the network of filaments. These bursts add to the diversity of stellar populations in NGC 1275, making it far more complex than a typical giant elliptical galaxy. The presence of the filaments also influences the flow of gas toward the central black hole. Some of the material within them may eventually lose angular momentum and sink inward, feeding the accretion disk. At the same time, the rising bubbles that help shape the filaments also prevent the majority of the gas from cooling uncontrollably. This delicate balance ensures that the core does not collapse into a runaway starburst, but instead sustains a regulated, steady cycle of cooling and feedback. The filaments therefore stand at the intersection of processes that govern both star formation and black hole activity. In the larger context of the cluster, the filaments extend far enough to interact with the surrounding plasma on scales of tens of thousands of light years. This makes them visible markers of how local processes within a galaxy can imprint patterns on the intracluster medium. Their shapes may trace the motion of bubbles, shocks or turbulence in the plasma, effectively acting as traces of forces otherwise invisible. In Perseus, where the X-ray emission is rich with ripples and cavities, the filaments provide a complementary view in cooler gas, highlighting the multi-scale nature of the cluster's central dynamics. Over cosmological timescales, the filaments may be transient, but during the epochs accessible to observation, they're among the defining features of NGC 1275. They demonstrate that the central galaxy is not quiescent, but actively cycling gas-forming stars and interacting with its environment. Their extraordinary length and persistence make them one of the most studied structures in any cluster, core a natural laboratory for exploring the coexistence of hot plasma-cold gas and stellar birth. In their faint glow and delicate outlines, they preserve the record of forces stretching across scales from the central black hole to the cluster medium, binding the story of NGC 1275 into the larger narrative of the Perseus Cluster. Beyond the striking filaments of gas and dust, another set of features emerges in NGC 1275. When it's studied in radio and X-ray light, the enormous radio lobes and bubbles inflated by jets from the galaxy's active nucleus. These structures are far larger than the stellar body of the galaxy itself, reaching tens of thousands of light-years into the surrounding intracluster medium. They are not composed of stars or ordinary gas, but of relativistic plasma particles accelerated to near the speed of light, which emit strongly at radio wavelengths. As these jets push outward from the central black hole, they displace the hot cluster gas, creating cavities that appear as dark voids in X-ray maps. The alignment between the radio lobes and the cavities demonstrates a direct causal link. The galaxy's nucleus injects energy into the cluster, sculpting the environment on vast scales. The bubbles are buoyant. Once inflated, they rise slowly through the hot plasma, similar to how air bubbles rise in water. As they move outward, they drag cooler gas with them, stretching it into filaments and mixing it with the intracluster medium. In Perseus, this process is especially well documented, with multiple pairs of cavities visible at different distances from the core. These represent successive episodes of jet activity, each one releasing energy and carving new voids. The result is a layered pattern of bubbles, ripples, and filaments that testify to the cyclical nature of the central engine. The age of the cavities can be estimated from their size and distance, showing that NGC 1275 has been injecting energy into the cluster for hundreds of millions of years. The energy contained in these bubbles is immense. By measuring their volumes and the pressure of the surrounding gas, astronomers can estimate how much energy was required to inflate them. In Perseus, the numbers reach values sufficient to offset the cooling of the intracluster medium in the cluster core. Without this feedback, the plasma would radiate away its heat and condense, leading to a massive burst of star formation. Instead, the jets maintain a balance, keeping the gas hot and extended. This balance is delicate, for too much heating would drive gas out of the core, while too little would allow uncontrolled cooling. The bubbles provide just the right amount of energy to sustain the cluster in a quasi-steady state regulated by the activity of the black hole. The shape of the bubbles provides insight into the interaction between jets and plasma. Some are round and symmetric, while others are elongated or distorted depending on how the jets encounter the surrounding medium. In Perseus, the bubbles are often surrounded by rims of brighter X-ray emission-marking regions where the gas has been compressed by the expanding plasma. These rims indicate the transfer of energy into the medium, heating it and driving weak shocks. In some cases, the bubbles appear connected to channels of radio emission that trace the paths of the jets, showing the direct route by which energy flows from the nucleus to the intra-cluster environment. The bubbles also generate sound-like waves in the cluster plasma. As they expand and move, they create pressure disturbances that propagate outward as ripples. Observed in X-ray images, these ripples appear as concentric arcs around the cluster core. They are evidence that the influence of the black hole extends far beyond the immediate vicinity, sending waves of energy across hundreds of thousands of light years. Although the period of these waves is tens of millions of years, they represent a form of mechanical feedback, redistributing energy throughout the cluster and preventing runaway cooling. The rise of bubbles is a slow process on human timescales, but significant in the life of a cluster. Over tens of millions of years, the plasma within the bubbles remains coherent as they drift outward, eventually mixing with the surrounding medium at greater distances. In Perseus, older bubbles can be seen farther from the core, partially faded but still visible as depressions in the X-ray glow. These ancient cavities are relics of past outbursts, each one a chapter in the long story of the galaxy's interaction with its environment. Together they show that the central black hole has been active, repeatedly shaping the cluster for a large fraction of its history. In addition to the primary bubbles, smaller cavities and channels are visible in high-resolution observations. These may represent secondary flows, side effects of the main jets, or regions where rising bubbles fragment. Their presence adds to the complexity of the cluster core, revealing a turbulent environment where gas is constantly being displaced, compressed, and mixed. Such turbulence further contributes to the stabilization of filaments and the distribution of heat. The interplay between bubbles, ripples, and turbulence forms a self-regulating system, with feedback maintaining the thermal state of the plasma. Radio observations provide a complementary view, showing the synchrotron emission from relativistic electrons spiraling in magnetic fields within the bubbles. This emission traces the internal structure of the lobes, revealing filaments, knots, and variations in brightness. The morphology of the radio lobes often matches the shape of the X-ray cavities, reinforcing the interpretation that they are filled with plasma from the jets. By studying the radio spectrum, astronomers can estimate the ages of the electrons, confirming that the bubbles correspond to different episodes of activity. In Perseus, these studies show a cycle of outbursts separated by tens of millions of years, consistent with the timescales inferred from cavity sizes. The impact of the bubbles extends beyond thermal balance. They also redistribute metals in the intracluster medium. As they rise, they drag enriched gas from the core outward, spreading elements forged in stars into the cluster environment. This mixing helps explain the observed distribution of metallicity, with higher abundances near the center, but significant enrichment at larger radii as well. In this way, the bubbles act not only as carriers of energy, but also as transporters of material, blending the products of stellar evolution into the larger cluster. The Perseus cluster is the clearest example of this feedback process because the bubbles are unusually prominent. In other clusters, similar features are seen but less distinctly. In Perseus, the brightness of the X-ray emission and the power of the central galaxy combine to create a textbook case of cavity inflation and feedback. This has made it a primary target for studies of how active galactic nuclei regulate cluster environments. The lessons learned here apply broadly across the universe, but nowhere are they as vivid as in the lobes and bubbles of NGC 1275. These enormous structures, invisible in ordinary starlight but brilliant in radio and X-ray, demonstrate that galaxies are not isolated islands. Instead, they are engines that can shape their surroundings on scales much larger than themselves. In Perseus, NGC 1275 does not merely sit at the cluster's center. It actively sculpts the medium, sustaining a balance between heating and cooling that defines the state of the cluster core. The bubbles and lobes stand as visible evidence of this ongoing influence, reminders that the dynamics of a single black hole can resonate across hundreds of thousands of light years. Surrounding the great cavities carved by radio lobes, the intra-cluster medium of Perseus reveals another layer of structure in the form of shock fronts and ripples. These features are subtle in appearance, yet significant in what they represent. High-resolution X-ray observations show faint concentric arcs around the central galaxy, spreading outward like the traces of long-forgotten waves. These arcs mark disturbances in density and temperature within the hot plasma, created by the repeated injection of energy from the core of NGC 1275. The black hole at the center does not release its power in a single event, but in cycles of outbursts, each one generating pressure waves that move through the surrounding gas. Over time, these waves carry energy away from the center, distributing it across hundreds of thousands of light years and preventing the plasma from cooling too quickly. Shock fronts in clusters like Perseus are not the violent supersonic shocks seen in supernova remnants, but gentler features often described as weak shocks or sound waves. Their Mach numbers, a measure of their strength, are only slightly above 1, indicating that the gas is compressed and heated modestly rather than explosively. Yet despite their subtlety, the cumulative effect of such shocks is profound. By propagating through the cluster core, they inject just enough heat to balance the radiative losses of the plasma. This balance ensures that the gas does not condense into a catastrophic cooling flow, which would otherwise deposit enormous amounts of cold gas and fuel starbursts far greater than those observed. The ripples extend outward from the galaxy's center in nearly circular patterns, though distortions reveal the influence of turbulence and irregularities in the surrounding medium. Their spacing corresponds to cycles of activity in the central black hole, with each ripple marking an episode when jets inflated bubbles and displaced the gas. The distance between ripples allows astronomers to estimate the timescale of these outbursts, often tens of millions of years. By mapping the sequence of ripples, researchers can reconstruct a long-term record of the galaxy's activity, stretching back hundreds of millions of years. In Perseus, this record is remarkably detailed, making it the best-studied example of such phenomena in the universe. The detection of these sound-like waves was a landmark in the study of galaxy clusters. It demonstrated that the influence of black holes could extend far beyond their host galaxies, shaping environments on scales comparable to those of entire clusters. In Perseus, the energy carried by the ripples is sufficient to balance cooling within the central region, establishing a form of mechanical feedback that maintains thermal stability. This finding resolved one of the major puzzles in cluster astrophysics, explaining why the predicted massive cooling flows are not observed. Instead of condensing, the gas is kept warm by a continual background of gentle heating delivered by these waves. Closer to the cavities, shock fronts appear more sharply defined, tracing the boundaries where expanding bubbles have compressed the plasma. These shocks are visible as bright rims in X-ray images, where the density and temperature of the gas are slightly higher. By measuring the jumps in temperature across these rims, astronomers can determine the strength of the shocks and the energy released in each event. In Perseus, these measurements confirm that the energy output of the nucleus is not only sufficient to inflate the bubbles, but also to heat the surrounding medium directly. The shocks distribute this energy more locally, while the ripples carry it outward in a more diffuse manner. Together they form a multi-scale network of feedback that regulates the state of the cluster gas. The propagation of ripples and shocks is influenced by the properties of the intracluster medium. The density, temperature, and viscosity of the plasma affect how waves move and dissipate. In Perseus, the plasma is hot and relatively dense, allowing the ripples to remain visible over large distances. Turbulence adds irregularities, distorting the arcs and creating variations in brightness. These irregularities provide information about the microphysics of the cluster medium, including the role of magnetic fields and the transport of heat. By studying the shapes of the ripples, astronomers gain insights into processes that cannot be replicated in laboratories on Earth. The importance of these features extends beyond Perseus. They serve as a template for interpreting other clusters where similar but fainter structures are observed. The clarity of the ripples in Perseus allows for detailed analysis, which can then be applied to systems where data are less complete. In this way, Perseus acts as a cosmic laboratory for feedback showing in detail how energy from a black hole can stabilize an entire cluster environment. The lessons learned here inform our understanding of galaxy formation and evolution across the universe, where feedback is essential to prevent runaway cooling and excessive star formation. Ripples and shocks are not static features but part of a dynamic process. As bubbles continue to rise and new ones are inflated, new waves are generated overlapping with older ones. This creates a layered pattern of disturbances, a palimpsest of activity that records the life of the black hole. Over millions of years, older ripples fade, blending into the background, while new ones emerge closer to the core. The persistence of these patterns shows that the feedback cycle is continuous, not an isolated event. NGC 1275 has been active for a large fraction of its life, and its influence has been felt throughout the cluster for hundreds of millions of years. The energy transported by these waves is vast, but it is delivered in a remarkably gentle way. Unlike explosive events that would disrupt the cluster, the ripples spread energy evenly, preserving the overall structure while maintaining balance. This subtlety is part of what makes them effective. They heat the gas without destroying the delicate networks of filaments and clouds. In Perseus, the coexistence of hot plasma, cool filaments, and young stars demonstrates that the system is finely tuned with feedback, preventing extremes while allowing complex structures to persist. Viewed together with the bubbles, the ripples and shocks complete the picture of how the central galaxy interacts with its environment. The jets create cavities, the cavities drive shocks, the shocks spread ripples, and the ripples heat the plasma. Each stage links to the next, forming a cascade of processes that begins with matter falling into the black hole and ends with energy distributed across hundreds of thousands of light years. This chain of events is visible in Perseus more clearly than anywhere else, making it the archetype for cluster feedback. The faint arcs of the ripples may be barely perceptible, but they carry the story of cosmic regulation written into the glow of the X-ray sky. Amid the vast filaments and expanding bubbles of NGC 1275, another population of objects comes into focus: the surrounding star clusters. These compact groupings of stars, often only a few light years across, appear scattered throughout the central galaxy and its extended halo. They are significant because they trace both the ancient history and the ongoing processes of star formation within the cluster's core. Star clusters are stable, long-lived systems that can endure for billions of years, making them valuable markers of past conditions. In NGC 1275, they are unusually abundant, and their variety points to multiple origins, some stretching back to the earliest epochs of the galaxy's growth, others forming more recently within the filaments of gas. Globular clusters form the oldest component of this population. These dense spherical collections of stars are among the first structures to form in a galaxy, and they preserve a record of the conditions of the early universe. In NGC 1275, thousands of globular clusters have been catalogued scattered across the halo and core. They glow with the faint red light of ancient stars, and their orbits extend into the diffuse light of the cluster. Some of them likely originated in smaller galaxies that were later accreted, captured during mergers, and now orbiting within the gravitational field of the central system. Their sheer number suggests a long history of accretion, with each infalling galaxy contributing clusters to the growing collection. Over time, this process has built a system far richer than what is found in typical galaxies, reinforcing NGC 1275's role as a central dominant galaxy in the Perseus Cluster. Superimposed upon these ancient populations are younger, bluer clusters that stand out in optical images. These younger clusters are often found along the filaments of cooler gas, confirming that star formation is still occurring in the hostile environment of the cluster core. Unlike the ancient globulars, these new clusters are irregular in their distribution, associated closely with the networks of dust and gas that thread across the galaxy. Their presence shows that the cycle of cooling, condensation and star formation is active even today, producing fresh stellar populations amid the turbulent medium. Though small compared with the total stellar mass of the galaxy, these clusters are important because they demonstrate that the feedback processes regulating the intracluster medium do not entirely suppress star formation. Instead, they allow it to proceed in localized bursts concentrated along filaments and knots where conditions permit. The young clusters are especially significant because they provide direct evidence of how gas flows from the intracluster medium into the galaxy. As radio bubbles rise and stretch filaments outward, gas cools and condenses, forming clumps dense enough to collapse into stars. Within these clumps, the formation of compact clusters is efficient, leading to bright blue concentrations that stand out against the red background of the older halo. These newly formed clusters are laboratories for studying how feedback and cooling interact, showing the direct link between processes on scales of tens of thousands of light years and the birth of individual stars. Star clusters also contribute to the enrichment of the surrounding gas. As massive stars within them evolve and explode as supernovae, they return heavy elements to the medium, enhancing its metallicity. This feedback cycle operates on smaller scales than the energy injection from the central black hole, but it adds detail to the larger picture of how matter cycles through the cluster. The combination of black hole feedback and stellar feedback creates a layered system with energy and material flowing at multiple scales simultaneously. In Perseus, the clusters act as both the products and contributors of these processes, their stars shining, while also preparing the medium for future generations. The distribution of clusters provides further insight into the assembly history of NGC 1275. Some groups are aligned with tidal features, streams of stars left behind by disrupted galaxies. These clusters were likely delivered during mergers, their orbits reflecting the paths of their parent systems. Others are spread more uniformly across the halo, suggesting that they have been in place for billions of years, long enough to mix thoroughly into the galaxy's potential. The combination of these populations reveals a layered history. Ancient clusters formed at the galaxy's birth, intermediate clusters, delivered by mergers, and young clusters forming in the present-day filaments. Together they present a continuum of star formation, stretching from the early universe to the current epoch. The properties of these clusters vary according to their ages and origins. Ancient globular clusters are metal-poor, meaning they contain fewer heavy elements, consistent with formation in the young universe before stars had produced significant enrichment. Clusters delivered by merging galaxies can be more metal-rich, reflecting the more evolved states of their parent systems. Newly formed clusters along filaments show the highest metallicities, enriched by the long history of star formation in the cluster core. By analysing these differences, astronomers can reconstruct the sequence of events that built the cluster system, linking stellar populations to the larger dynamics of the Perseus Cluster. The sheer number of clusters around NGC 1275 also influences its appearance. In deep images, the core of the galaxy is peppered with point-like sources, each a compact cluster shining with thousands to millions of stars. Their combined light adds texture to the galaxy's halo, making it appear speckled rather than smooth. This richness sets NGC 1275 apart from typical ellipticals, which often have far fewer clusters. The abundance of clusters testifies to the unique role of the galaxy as the central hub of a massive cluster, where mergers and ongoing star formation combine to produce an extraordinary population. Clusters also serve as dynamical tracers. By measuring their motions, astronomers can probe the mass distribution of NGC 1275 and its surrounding dark matter halo. The velocities of clusters orbiting at large radii provide information about the gravitational potential far beyond the reach of starlight. In Perseus, such studies confirm that the galaxy sits within a deep well, dominated by dark matter consistent with the broader cluster potential. The clusters, therefore, are not only records of star formation, but tools for measuring the invisible framework that supports the entire system. The contrast between the oldest and youngest clusters in NGC 1275 underscores the complexity of its evolution. Most central cluster galaxies are dominated by old populations, but here new clusters continue to form alongside ancient ones. This coexistence highlights the delicate balance maintained by feedback. Without the regulation provided by jets and bubbles, the cooling of the intracluster medium would be catastrophic, forming stars at unsustainable rates. With feedback, however, cooling is moderated, allowing star formation to proceed in measured bursts that create small clusters rather than overwhelming starbursts. The result is a galaxy that contains both the fossil record of the early universe and the living evidence of present-day activity. In summary, the star clusters of NGC 1275 provide a window into its layered history and ongoing transformation. They include ancient globulars formed at the dawn of the galaxy, intermediate populations delivered by mergers, and young clusters born in the filaments shaped by feedback. Their numbers, distribution and properties reflect the interplay between accretion cooling and regulation in the cluster core. As long-lived and luminous markers, they record the passage of billions of years, while also testifying to the processes unfolding in the current epoch. Within the broader Perseus cluster, these clusters are not isolated curiosities, but integral components of the feedback cycle that connect stars, galaxies, and plasma on the largest scales. While the filaments and clusters provide vivid signs of star formation, another key component of NGC 1275's environment lies in its vast reservoirs of molecular gas. These cold clouds, composed primarily of molecular hydrogen, represent the raw material from which new stars are built. Unlike the hot plasma that fills the cluster, or the diffuse warm gas that glows in emission lines, molecular gas is hidden from direct view in visible light. It is instead traced through emissions from molecules such as carbon monoxide, which radiate at millimeter wavelengths. Observations with radio and submillimeter telescopes have revealed that NGC 1275 contains enormous stores of such gas, concentrated in and around its central regions, but also extending along filaments that stretch outward into the intracluster medium. The presence of this molecular gas is remarkable, because the core of a galaxy cluster is generally a hostile environment for such cold material. Temperatures in the surrounding medium reach tens of millions of degrees Celsius, a regime in which molecules should not easily survive. Yet in NGC 1275, not only do molecules persist, they exist in vast quantities, hundreds of millions of solar masses worth of material. This persistence suggests that the gas is continuously replenished, most likely from cooling flows within the intracluster plasma. As parts of the hot medium radiate away energy, they cool and condense, forming clouds dense enough for molecules to assemble. These clouds are then drawn inward by gravity, feeding both the central black hole and regions of star formation. The distribution of molecular gas is complex. Some is located in the immediate surroundings of the central galaxy, forming rings and clumps close to the core. Other reservoirs extend along the filaments embedded within the long threads of cooler gas seen in optical light. The alignment between molecular gas and filaments suggests a direct connection. As bubbles rise and lift gas outward, filaments stretch into the cluster medium, carrying with them cold clouds. Within these filaments, molecular gas condenses into denser knots, which may then collapse to form stars. Thus, the molecular reservoirs are both the products of feedback and the fuel for ongoing activity linking processes on scales of tens of thousands of light years to the intimate physics of star formation. The mass of molecular gas in NGC 1275 is exceptional for a central cluster galaxy. While many giant ellipticals contain little or no cold gas here, the amounts are large enough to sustain measurable rates of star formation. Observations suggest that the galaxy forms stars at a rate of tens of solar masses per year, far higher than in most other ellipticals. This activity is concentrated in the filaments and dust lanes where molecular gas is densest. The star clusters observed along these structures are direct evidence of this ongoing process. In this way, the molecular gas ties together the cycles of cooling, accretion, and feedback that define the cluster core. The conditions within the molecular gas clouds are also shaped by their environment. Magnetic fields thread the filaments, providing additional support against collapse. Turbulence from the surrounding plasma influences their structure, compressing some regions while dispersing others. Radiation from nearby stars and the active nucleus ionizes the outer layers, creating envelopes of warmer gas around cold cores. This multiphase structure allows molecular gas to survive longer than it otherwise would, protected within insulated regions while still interacting with its surroundings. The survival of such gas in the hostile cluster core is a delicate balance, requiring the combined effects of shielding magnetic confinement and continual replenishment. In addition to hydrogen and carbon monoxide, other molecules have been detected in NGC 1275, including more complex species such as hydrogen cyanide and formyl ions. These detections demonstrate that chemical processes are active even in this extreme environment. The presence of such molecules indicates regions of high density, where collisions between atoms and molecules allow chemistry to proceed. These molecules act as tracers of conditions within the gas, providing information about density, temperature, and radiation levels. Their abundance helps refine models of how gas cools and condenses in the cluster environment. The role of molecular gas is not limited to star formation. It also serves as the primary source of fuel for the central black hole. As clouds sink toward the core, some of their material is captured by the accretion disk, where it is heated and accelerated before crossing the event horizon. The energy released in this process powers the jets and bubbles that reshape the cluster medium. Thus, the molecular gas is at the heart of the feedback cycle. Cooling plasma forms molecular clouds. Clouds feed the black hole. The black hole injects energy into the plasma, and the cycle repeats. The persistence of molecular gas in NGC 1275 demonstrates that this cycle is ongoing and finely balanced. The interplay between cooling and feedback is evident in the spatial distribution of the molecular gas. Rings and arcs near the core suggest that inflowing gas has been shaped by the dynamics of the central engine. Filaments farther out show the imprint of bubbles lifting gas from the center. The combination of these features reveals the simultaneous operation of inflow and outflow, with gas cooling and sinking, even as other gas is raised outward by feedback. The molecular reservoirs are embedded in this dynamic environment, constantly renewed and constantly consumed. Over long timescales, the molecular gas reservoirs evolve. Some clouds are consumed in star formation, locking their material into long-lived stars. Others are accreted by the black hole, their mass converted into energy that heats the cluster. Still others are disrupted or evaporated by turbulence and radiation, mixing back into the hotter medium. Each of these pathways contributes to the overall cycling of matter in the cluster core. The balance between them determines whether star formation continues, whether feedback remains effective, and whether the cluster as a whole remains stable. NGC 1275 illustrates this balance more clearly than almost any other system. Its molecular gas reservoirs are vast and active, its star formation is ongoing, and its black hole is powerful. The interaction of these components creates a complex self-regulating system, where matter moves through different phases in an endless cycle. The coldest molecular clouds hidden from view in ordinary light are thus central to the story of the Perseus Cluster. They represent both the beginning of stars and the fuel of feedback, the fragile yet vital component that links processes from the smallest scales of molecular chemistry to the largest scales of cluster dynamics. Moving inward from the sprawling filaments and molecular reservoirs, the structures around the central regions of NGC 1275 take on more compact and intricate forms. Here the gas and dust arrange themselves into inner filaments and ring-like features that are closer to the galaxy's luminous core. These structures are shorter and denser than the great threads that extend tens of thousands of light-years outward, yet they are equally significant because they trace the transition between the extended halo and the immediate vicinity of the nucleus. Observations reveal loops, arcs, and partial rings of gas, some illuminated by young stars, others glowing in emission lines as they interact with radiation and plasma. Their shapes suggest that the forces shaping them are more complex than those that govern the larger outer filaments. Gravitational potential, turbulence, magnetic fields, and the outbursts of the black hole all combine to sculpt these inner patterns into delicate arcs and streams. These features are often most clearly seen in optical and ultraviolet wavelengths, where they emit strongly in hydrogen lines. They appear as wisps of reddish light around the bright core, wrapping partly around the center in curving arcs. Some of them form ring-like structures, incomplete circles that may represent gas settling into rotational equilibrium or the remains of material disturbed by past outbursts. Others are more linear, pointing toward the nucleus, as if funneled inward by gravity. Their relatively compact scale, spanning only a few thousand light-years compared with the tens of thousands of the larger filaments, makes them more directly connected to the core processes of the galaxy. The dynamics of these inner features are shaped by both inflow and outflow. On the one hand, gas cools from the intracluster medium and condenses into filaments that move toward the nucleus. On the other hand, jets and bubbles from the central black hole disturb and lift gas outward. The result is a region where flows converge, sometimes colliding, sometimes wrapping around one another and sometimes being stabilized into ring-like distributions. Spectroscopic studies show a range of velocities within these structures, with some gas moving inward at hundreds of kilometers per second, and other regions showing evidence of being pushed outward. This complexity reflects the constant tension between accretion and feedback in the cluster core. Star formation is also evident in these inner filaments and rings. Compact blue clusters of young stars are found embedded in the gas, especially in regions where the density is highest. Their light illuminates the surrounding material, creating knots of brightness within the filaments. These clusters are younger than those found farther out in the halo, indicating that star formation is proceeding continuously at multiple radii within the galaxy. The stars forming here are close enough to the nucleus that their environment is shaped not only by the gas but also by radiation and energetic particles from the black hole. This makes them unique laboratories for studying how stellar birth proceeds in extreme conditions. Dust is present in these inner regions as well, often intertwined with the gas filaments. In optical images, dust appears as dark lanes crossing the bright starlight, while in infrared it glows faintly as it absorbs and re-radiates energy. The dust helps shield parts of the gas from radiation, allowing molecules to survive and star formation to continue. At the same time, dust itself is constantly at risk of being eroded by the energetic environment, so its persistence suggests continual replenishment, likely through inflow of fresh material from the outer cluster medium or from minor mergers with smaller galaxies. The combination of dust and gas gives the inner structures a layered multi-phase character that contrasts with the smooth stellar background of the bulge. The ring-like features are particularly intriguing. Some appear to encircle the nucleus at distances of several thousand light-years, suggesting they may be linked to rotational dynamics. If gas falls inward with angular momentum, it cannot plunge directly into the center, but instead settles into orbit, creating rings or disks. Over time, these rings may fragment into filaments under the influence of instabilities or external disturbances. In NGC 1275, the rings are not perfectly symmetric, but warped and broken, reflecting the turbulence of their environment. Nevertheless, their existence points to a process by which gas transitions from large-scale inflow to more ordered structures near the core. High-resolution observations reveal that some of the inner filaments connect directly to the base of the larger outer structures. These connections suggest that material is continuously flowing inward bridging scales, from tens of thousands of light-years down to a few thousand. The inner filaments thus serve as the final channels guiding gas toward the nucleus. Along the way, parts of the gas are consumed in star formation, while other parts continue inward to feed the accretion disk. The efficiency of this transport system determines how much material reaches the black hole and how much is locked into stars. The balance between these pathways influences both the luminosity of the active nucleus and the growth of the galaxy's stellar population. The motions of the inner gas also provide clues about the gravitational potential of the central regions. By measuring Doppler shifts in the emission lines, astronomers can map the velocities of the filaments and rings. These velocities indicate the presence of a deep gravitational well consistent with the mass of both the galaxy's bulge and its central black hole. In some regions, the motions show signs of rotation hinting at the presence of a disk-like structure. In others, the gas appears chaotic with inflow and turbulence dominating. The mix of ordered and disordered motion illustrates the complex interplay of forces in the galaxy's inner environment. The interaction between gas-dust stars and feedback in these regions is a microcosm of the cluster core as a whole. Cooling draws material inward, feedback pushes it outward, and star formation proceeds in the spaces between. The inner filaments and rings are where these processes overlap most directly, leading to the coexistence of opposing flows and structures. Their persistence over long timescales shows that a delicate balance is maintained, allowing both accretion and feedback to continue without either dominating completely. The importance of these inner features lies not only in their beauty but in their function. They are the pathways through which matter moves from the larger cluster environment into the very center of NGC 1275. They regulate how much gas reaches the nucleus, they host the formation of new stars, and they preserve a record of the dynamic forces shaping the core. Without them, the connection between the outer cluster medium and the inner black hole would be less direct. With them, the processes of cooling, accretion, and feedback are visibly linked across scales, forming a chain that ties together the evolution of the galaxy and the cluster it inhabits. As attention moves further inward, the bright stellar bulge and dense core of NGC 1275 come into view. This central region is dominated by the light of billions of stars packed tightly together, forming the heart of the galaxy. Unlike the outer halo, which is diffuse and faint, the bulge glows intensely, its starlight overwhelming the view and obscuring fainter structures. The stars here are mostly old low-mass stars that shine with a reddish hue similar to those in other elliptical galaxies. Yet embedded within this sea of ancient light are irregularities that hint at more recent activity pockets of younger stars, threads of gas, and dusty patches that cross the luminous background. Together, these features show that the bulge of NGC 1275 is not a static relic, but an active participant in the galaxy's ongoing evolution. The density of stars in the bulge is extreme. Moving toward the nucleus, the number of stars per cubic light-year increases dramatically, creating an environment where gravitational interactions are frequent and orbits are complex. This concentration of mass exerts a strong gravitational pull, not only on stars but also on gas and dust, guiding their motions and funneling material inward. The bulge acts as both a reservoir of old stellar populations and a gateway to the central black hole, linking the large-scale structure of the galaxy to its innermost processes. The motions of stars within the bulge provide valuable information about the galaxy's mass distribution. By measuring their velocities, astronomers can infer the depth of the gravitational potential and estimate the mass of the central regions. These studies confirm that NGC 1275 contains a supermassive black hole at its heart, with a mass of hundreds of millions of solar masses, consistent with the bulge's luminosity and dynamics. Although the bulge is dominated by old stars, it's not entirely quiescent. Observations reveal that young stellar clusters are also present, particularly in regions where filaments of gas extend into the core. These clusters shine with blue light contrasting sharply with the surrounding reddish glow. Their presence indicates that star formation is occurring even in the dense, high-radiation environment near the nucleus. Such star formation is likely triggered by the inflow of cold gas along filaments, which condenses into clouds dense enough to collapse despite the surrounding heat and turbulence. The result is a layered stellar population, with the bulk of the bulge composed of ancient stars, but with younger generations sprinkled throughout. Gas is also present in the bulge, though in smaller amounts compared to the extended filaments. Ionized gas glows in emission lines tracing arcs and knots that weave through the stellar background. Some of this gas is falling inward, feeding the nucleus, while other parts are disturbed by feedback pushed outward by shocks and turbulence. Dust accompanies the gas, appearing as dark streaks that block the light of stars behind them. In infrared observations, this dust glows faintly, adding another layer of complexity to the central regions. The combination of stars, gas, and dust creates a rich texture far from the smooth, featureless bulge typical of giant ellipticals. The core of NGC 1275 also exhibits structural asymmetries that reflect its dynamic history. Minor mergers with smaller galaxies have deposited stars and gas into the central regions, leaving behind irregularities in the stellar distribution. Tidal forces from these encounters can warp the bulge, creating shells or ripples that linger for hundreds of millions of years before being smoothed out. Deep imaging sometimes reveals such faint features, subtle reminders that the bulge has been shaped not only by internal evolution, but also by external accretion. These irregularities add to the evidence that NGC 1275 is still assembling even in its core. The kinematics of stars in the bulge provide further clues. Many stars follow random orbits consistent with the dynamics of an elliptical galaxy. However, some show evidence of ordered motion possibly linked to the rotation of gas or the influence of past mergers. Spectroscopic measurements reveal gradients in velocity and dispersion, indicating that the bulge is not perfectly relaxed. Such deviations from symmetry point to ongoing processes where new material is still being added and mixed into the central structure. This dynamical complexity makes the bulge of NGC 1275 more active and varied than those of more isolated galaxies. The intense radiation environment of the bulge also shapes the fate of gas and dust. Ultraviolet light from young stars and energetic emission from the active nucleus ionize nearby clouds, producing bright knots visible in optical emission lines. These knots outline regions where gas is being excited or heated, often along the edges of filaments that reach into the core. At the same time, the harsh radiation can erode dust grains, reducing their lifetimes. The persistence of dust in the bulge indicates that it is being replenished, either from inflow along filaments or from stellar processes such as supernovae and winds. This constant turnover ensures that the bulge remains chemically enriched and dynamically active. Embedded in the very center of the bulge is the dense stellar cusp that surrounds the black hole. Here star densities reach their highest values with orbits tightly bound to the gravitational influence of the central mass. This cusp provides the transition between the galaxy's stellar body and the accretion-dominated nucleus. Stars in this region move at extreme velocities, their orbits distorted by the deep gravitational potential. Observations of their motion help refine estimates of the black hole's mass and provide evidence for the extraordinary conditions in the galaxy's core. The coexistence of dense stellar populations with gas and dust in this cusp highlights the complexity of the environment just outside the event horizon's reach. The bulge also serves as a reservoir of chemical enrichment. Over billions of years, supernovae from massive stars have seeded the central regions with heavy elements. These metals enrich the gas, influencing its cooling rates and chemistry. The high metallicity of the bulge gas contrasts with the lower abundances found farther out in the cluster, reflecting the long history of stellar evolution concentrated in the galaxy's center. This enrichment shapes the conditions for future star formation, ensuring that new stars born in the bulge contain heavier elements than the ancient populations that dominate its light. In the broader context of the Perseus Cluster, the bulge of NGC 1275 is the gravitational and luminous centerpiece. It anchors the galaxy, providing the mass and depth of potential needed to hold the surrounding structures together. It connects to the halo through tidal features and streams, to the filaments through inflowing gas, and to the nucleus through the funneling of material. The bulge is not an isolated entity, but part of the continuum linking scales from the cluster environment to the central black hole. In its dense stars, irregular gas and embedded dust, it records the interplay of processes that define the galaxy's present and future. At the very center of NGC 1275 lies the active galactic nucleus, the powerhouse that drives many of the features seen throughout the Perseus Cluster. This nucleus is built around a supermassive black hole with a mass of hundreds of millions of times that of the Sun. Although the black hole itself is invisible, its presence is revealed through the extraordinary phenomena it produces. Matter drawn into its deep gravitational well forms an accretion disk, a swirling structure of gas heated to extreme temperatures as it spirals inward. Friction turbulence and magnetic fields within the disk convert gravitational energy into radiation, making the nucleus of NGC 1275 one of the most luminous regions of the galaxy, across a wide range of wavelengths. The accretion disk radiates in ultraviolet and X-ray light, but its effects extend far beyond its immediate environment. From the inner regions, twin jets of relativistic plasma are launched outward, piercing through the surrounding galaxy and into the intracluster medium. These jets are responsible for inflating the vast radiolobes and bubbles, observed tens of thousands of light years from the core. The jets are highly collimated near their origin, but gradually spread as they move outward, transferring energy from the smallest scales near the black hole to the largest scales of the cluster. This process links the physics of accretion to the dynamics of an entire galaxy cluster, showing how central black holes regulate their environments. The nucleus of NGC 1275 is classified as a Seyfert galaxy in the optical band and as a powerful radio source in longer wavelengths. Invisible light emission lines from ionized gas reveal the intense radiation field near the black hole. These lines come from clouds of gas orbiting in the broad line and narrow line regions, where radiation ionizes atoms and produces characteristic spectra. In radio, the nucleus shines as one of the brightest sources in the sky, known historically as Perseus A. The synchrotron radiation emitted by relativistic electrons spiraling in magnetic fields makes the jets and lobes luminous across vast distances. In X-ray and gamma-ray bands, high-energy processes near the black hole and within the jets add further emission, making NGC 1275 one of the most studied active galactic nuclei in the nearby universe. The structure of the central engine is layered. Closest to the black hole is the accretion disk, rotating at enormous speeds and radiating energy. Surrounding this disk is a torus of dust and gas which absorbs and re-emits radiation, especially in the infrared. Beyond the torus are the ionized gas clouds that create the emission lines, observed in optical spectra. At larger scales, the jets dominate, carrying energy far beyond the galaxy. Each layer interacts with the others, and together they create the composite appearance of the active nucleus. Observations across the spectrum from radio interferometry to X-ray spectroscopy provide a detailed map of these structures and their effects. The variability of the nucleus is another hallmark of its activity. Over timescales of days to years, its emission fluctuates as the accretion rate changes and as instabilities in the disk evolve. Such variability is common in active galactic nuclei, reflecting the dynamic nature of gas falling into a black hole. In NGC 1275, monitoring campaigns have recorded changes in brightness across multiple bands, linking events in the core to responses in the surrounding environment. These observations help constrain models of how material flows through the accretion system and how jets are powered and maintained. The feedback from the active nucleus is not limited to mechanical energy in jets. Radiation from the accretion disk also ionizes and heats gas in the surrounding regions. This photoionization is responsible for the bright emission lines seen in the galaxy's spectrum. It also influences the chemistry of molecular clouds, altering their stability and cooling rates. Radiation pressure can push dust outward, contributing to the distribution of material in the core. Together with the jets, this radiative feedback ensures that the influence of the black hole is felt throughout the central galaxy and beyond. The black hole's growth is intimately tied to the supply of molecular gas in the cluster core. As clouds sink inward along filaments, some fraction reaches the accretion disk and adds to the mass of the black hole. Over billions of years, this steady feeding has built the nucleus into its current scale. At the same time, the feedback from the black hole regulates how much gas can continue to cool and fall inward. This self-regulation prevents unchecked growth, creating a balance where the black hole and the cluster medium evolve together. In Perseus, the clarity of this cycle is exceptional, making NGC 1275 a benchmark for studies of black hole galaxy coevolution. Magnetic fields play a crucial role in the workings of the nucleus. They thread the accretion disk, extracting rotational energy and channeling plasma into jets. Without magnetic fields, the jets could not be launched or collimated. Their presence explains the remarkable coherence of the jets, which maintain their direction across tens of thousands of light years. Polarization studies in radiolight reveal the alignment of these fields, providing direct evidence of their role in shaping the nucleus's output. The interplay of gravity, rotation, and magnetism defines the structure of the active nucleus and its impact on the cluster. The sheer luminosity of the nucleus is striking. Although it occupies only a tiny fraction of the galaxy's volume, it outshines vast regions of stars. Its radiation spans from radio to gamma rays, a testament to the diverse processes operating near the black hole. Yet despite this intensity, much of its energy is not radiated away, but injected mechanically into the cluster through bubbles and ripples. This efficiency ensures that the energy released by accretion is not wasted but redistributed, stabilizing the intracluster medium. In this way, the nucleus serves as both a beacon and a regulator, a compact source whose influence extends across hundreds of thousands of light years. NGC 1275's nucleus is therefore both ordinary and extraordinary. Ordinary because it follows the same principles as other active galactic nuclei accretion jets feedback. Extraordinary because its effects are seen so clearly in the surrounding cluster, creating cavities, ripples, filaments, and star clusters that bear its imprint. Its study has advanced understanding of how black holes shape galaxies and clusters, making it a cornerstone system in astrophysics. At the center of the Perseus Cluster, the nucleus of NGC 1275 stands as the point where cosmic scales converge the smallest structures of accretion, connecting seamlessly to the larger structures of a galaxy cluster. Within the innermost environment of NGC 1275, where the bulge fades into the glare of the active galactic nucleus, the interplay of matter and energy reaches its most extreme. Here, gas-dust stars and magnetic fields coexist in a turbulent region dominated by the gravity of the central black hole. The scale is small compared with the filaments and cavities that stretch tens of thousands of light-years outward, yet the impact is far greater. This region, only a few hundred to a few thousand light-years across, is where inflowing material is finally captured, heated and transformed, fueling the processes that regulate the entire Perseus cluster. The environment is harsh, radiation fields are intense, particles are accelerated to relativistic speeds, and the balance between inflow and outflow is precarious. Gas that reaches this inner domain has already travelled a complex path, drawn from the intracluster medium condensed into filaments, and funneled inward through rings and streams. It now faces the final gravitational descent. Some of it collects into dense molecular clouds orbiting close to the center, while other material continues spiraling inward toward the accretion disk. Along the way, turbulence, magnetic fields, and shocks fragment the gas into clumps, some of which collapse into young stars even in the immediate neighborhood of the black hole. This coexistence of stellar birth with accretion and feedback highlights the extreme conditions under which different processes overlap. Stars forming here are bathed in radiation from the nucleus, and yet their clusters manage to shine amid the glare. The immediate surroundings of the black hole are dominated by the accretion disk, a structure only light days to light months across, invisible to direct observation at these distances, but inferred from emission across the spectrum. Around it, a corona of hot plasma emits X-rays, while farther out obscuring clouds and dust absorb and re-radiate energy in the infrared. Jets erupt from the poles of the black hole, carving their way through this environment and transporting energy outward. All of these layers interact with the surrounding bulge and halo, ensuring that no part of the galaxy remains unaffected by the nucleus. Even small variations in the accretion rate can ripple outward, as shocks, bubbles, and waves that shape the cluster on scales many orders of magnitude larger. Close to the nucleus, the gravitational field is so strong that stellar orbits curve sharply, with velocities of hundreds of kilometers per second. Some stars may even be captured and consume their matter, torn apart and accreted by the black hole. Tidal forces dominate stretching, compressing material that ventures too near. Observations of emission lines from gas in this region show broad-profile signatures of gas, moving at enormous speeds close to the event horizon. These broadline regions are unique to active galactic nuclei, revealing conditions that cannot be replicated elsewhere in the universe. In NGC 1275, they confirm the presence of a powerful accreting black hole, the ultimate engine of its activity. Magnetic fields shape the innermost flows as well. Twisting around the accretion disk, they channel plasma into narrow jets that emerge perpendicular to the disk's plane. These jets, though narrow at their base, contain immense amounts of energy and momentum. They pierce through the immediate surroundings, pushing aside gas and dust, and eventually inflate the giant radio lobes seen far beyond the galaxy. The energy transfer begins here at sub-parsec scales, where magnetic fields convert rotational energy into directed outflows. This mechanism connects the physics of black holes to the astrophysics of galaxy clusters, bridging scales from the size of the solar system to millions of light years. Radiation pressure also plays a role in shaping the inner environment. Light from the accretion disk is so intense that it can push against dust and gas driving outflows that compete with inflows. These winds are less collimated than jets, but contribute to the redistribution of material in the core. They may carry enriched gas outward, adding to the metallicity of the intracluster medium. At the same time, radiation ionizes nearby gas, producing luminous emission lines that make the nucleus one of the brightest features in the optical spectrum of Perseus. These lines provide diagnostic tools for understanding density, temperature, and motion within the innermost clouds. Despite its small size, this region is not isolated from the rest of the cluster. The energy it releases in radiation jets and winds sets the conditions for the entire Perseus system. Without it, the intracluster medium would cool, rapidly collapsing into dense flows and forming stars at rates far higher than observed. With it, the plasma is reheated, cavities are inflated, and ripples distribute energy across vast distances. The stability of the cluster core depends on the balance maintained here in the immediate surroundings of the black hole. NGC 1275 is thus both a local galaxy and a cluster-scale regulator, its core influencing matter on scales millions of times larger than itself. Variability in the nucleus underscores the dynamic nature of this environment. Bursts of activity launch new jets and inflate new cavities, while quieter phases allow cooling and inflow to proceed. This cycle is repeated many times over hundreds of millions of years, leaving behind the layered structures seen in the cluster today. Each new outburst resets the balance, preventing runaway cooling but never fully halting star formation. The persistence of filaments, bubbles and clusters shows that the system operates in a delicate equilibrium, with inflow and feedback never completely dominating one another. On the smallest scales close to the event horizon, matter is accelerated to near the speed of light and swallowed by the black hole. Energy released in this process emerges in forms that affect the cluster as a whole. Though invisible directly, the consequences are plain in the vast structures around the galaxy. The immediate environment of the nucleus is therefore both the endpoint of inflowing matter and the origin of feedback that sustains the cluster. It is the pivot point around which the history of Perseus turns the place where the cosmic web connects to the physics of relativity. In the innermost environment of NGC 1275, one sees the culmination of processes that begin far beyond the galaxy itself. Gas cooling from the cluster medium drawn inward by gravity survives as filaments condenses into molecular clouds, forms stars and finally feeds the black hole. The black hole responds with jets radiation and winds which reshape the medium, regulate cooling and sustain equilibrium. Every feature of the cluster core, the cavity's ripples, filaments, rings and star clusters ultimately ties back to this central region. It is the smallest domain in scale, yet the largest in influence, a reminder that the fate of galaxies and clusters can hinge on what happens within a few light years of a black hole.